So here's an example of a problem where you need to do both energy conservation and circular motion in order to come up with a final solution. The final solution to this problem is if we have a roller coaster like the Mindbender at Six Flags. If you've been to Six Flags, I guess many of their many of their roller coasters now have loop-to-loops. But suppose we have a loop that has to be gone around, and the loop has a radius r, and the car is not powered, and we'll approximate it to be frictionless. So the problem is, from what height h do we have to release the car in order for it just to make it around the top of the loop? Now, I will point out to you that you better take it from higher than 2r, because otherwise, when it got to the top, it would simply be at rest, because it's from energy conservation. If it started from a height 2r, the next time it got up to a height 2r, it would have to be at rest again. So it has to have some minimum velocity in order to make it through. Otherwise, it would come off the track somewhere before you got to the top. Actually, we'll talk about that maybe a little bit later. I'll assign for you to give a try to figuring out if you dropped it from 2R, where would it come off the track. So let's proceed here. And let's first of all ask ourselves, as you always should if you are wondering whether the energy of a system is conserved, whether you can use energy conservation or not, is you have to ask yourself, are there any external forces doing work on the little car as it goes through its journey? And the answer is yes, indeed. There is an external force, okay? That's like this, and that would be the normal force. So here is the normal force that the track exerts on the car as it goes along. But the normal force is always perpendicular to the distance that the car is traveling, and so the normal force does no work. Therefore, the energy is conserved of this system. And so we say, what is the initial energy of the system? Okay, it's E1, and that's mgy, where m is the mass of the car. E2, the time we're interested in it, is when it's at the top of the loop, and now its gravitational potential energy is mg times 2r, because it's at a height of 2r above where I have chosen y to be 0. But it also has some kinetic energy, plus 1/2 mv squared. And this has to be, since the energy is conserved, has to be equal to mgy. So it doesn't make any difference what the load is, because the m's you see here all cancel out. And so what we're left with is 2gr plus 1/2 v squared equals, oops, made a little mistake here. This is mgh, right? Same true here. mgh. Okay, y is equal to h at the beginning. Okay, so this is equal to gh. So what we have here basically is one equation with two unknowns. The unknowns are h, which is the object of the game, but we also don't know what v is. That's the circular motion part of the problem. So I'm going to choose a body. Okay, so here is the cart. That's my body, and it's at the top, so I've drawn it upside down here. I'm going to ask myself, what are all the forces on this body? Well, there is its own weight, mg, and there is a normal force, N. So the sum of the forces, let's call this the plus x direction here. Okay, so the sum of all the forces in the x direction is equal to, well, what is it? It's N plus mg. And that has to be equal to ma, but a, of course, is v squared over r. Okay, so let's have a look at what we have here. We have that the bigger v is, the bigger n is. So as v goes smaller and smaller, the normal force is going to get smaller and smaller until eventually, when n equals 0, we're going through this loop as slowly as we possibly can, right? So when n is equal to 0, we're going through as slow as we possibly can, and so that's going to give us the critical v. So what I find then is that v squared is equal to gr. And maybe I should call that v sub minimum or something like that, but that's the slowest speed that you can go through. If you're going through at that speed, then your centripetal force, which is giving you your centripetal acceleration, is your weight. And you can't, if you go through any slower, you need to essentially have n be negative. But we're assuming here that the track can't pull on you, it can only push on you. I should tell you, in the real world, just for safety's sake, the car is not able to come off the track, so if something goes wrong and you end up at rest at the top, you'll hang there, okay, you won't fall to the bottom. Okay, so what we need to do now is finish the problem. Now that we have what v squared is, we can take that back into this equation here, which is the energy equation. And so let's put that in. And so I have 2gr plus 1/2 gr equals gh. And you see the g's cancel out. And so h is equal to 5/2 r. And that's it. So you have to drop it from 2.5 r. Okay, you have to go another 1/2 r up. Of course, in the real world, you have to drop it from higher than that, because in the real world there's friction and the energy won't be completely conserved. So, as I said earlier, I would suggest that you try the following. This is a little bit of a tricky problem. See if you can find the following. If you drop it from h equals 2r, where will it come off the track? Okay? Good luck with that.